The following content is for entertainment and educational purposes only. It does not constitute means for diagnosis, healthcare advice, nor treatment. Make use of a qualified healthcare professional for such purposes.
Hello, everyone. My name is Dr. Charlene Ortiz, and today we are going to talk about frequency data. More specifically, we are going to talk about the chi-square. We're going to talk about the elements of what does that look like, what does it help us do, and more importantly, we're going to cover some examples that are related to the field of social sciences. So let's get started. All right. So one of the first things that I would like to mention is that in regards to frequency data, when we are looking at what frequency data is, I need you to remember that frequency data involves that of a tally. So whenever you hear the term frequency data, we're looking into the amount of something. So for example, the frequency of a score. Think about whenever you're taking a test and the frequency of that number being such. Therefore, when we think about frequency, I do need you to remember that it refers simply to the tally of observations, the tally of that data set. Now, one of the ways that we can use frequency data is that it allows us for the comparison of different groups. It allows us for instance, we can think about a two-group comparison, such in the case here. We can also look into the selection of multi-group comparison. And what do I mean? For example, let's look at this illustration here. So for instance, when we are talking about frequency, let's think about the amount of people, for example, that take medication A. So for example, the one that is the red pill, medication B. So for example, one group that takes the medication, the red medication, and then another group that takes the second medication. So notice how we can do a comparison of two groups. By the same token, if we move back to our illustration here, notice that we can do a multi-group comparison. So in this case, we will have the selection in our illustration, I should say. Think about the instance of where there could be a multi-group comparison. So for instance, the group of people who took one medication, the red pill, another medication, the blue pill, green, and the yellow. So notice that we can also do a multi-group comparison. In addition, frequency data allows us to do the observation, that tally of independent groups. So something important that I need to remind you of is whenever we are doing an observation, whenever we are looking into independent groups, what we're trying to do is looking into that interaction, seeing if there's an interaction upon that tally, right? So think about the interaction. If we go back to our slides, think about selecting said pill, and the selection is going to depend upon the sex of that patient, that client, or that research participant. So notice that in this case, when we're looking into an independent group, we're looking to see if there's any interactions. For example, if females have an interaction in the sense that their sex allows for, say, more of a preference of selecting the red pill, or for example, if there's still an interaction with sex with males. So for instance, is there an interaction between being a male and selecting, having a preference, for example, of using or selecting that blue pill? So notice that frequency data will allow us to view those types of comparisons, either by two groups multi-group, or because there is an independent group in this case. So for example, we are referring to females and males. Now, in keeping with this example, notice that now we need to look into frequency and the chi-square. Now, when we're looking into chi-square, I need you to remember that this will be the symbol for chi-square. We're actually going to cover that a little bit more in detail later on. So let's look into the understanding of the chi-square. Well, first of all, in order to conduct that chi-square, we will need to determine what number of categories or cells do we want to include. So for example, let's go back to our previous example here. Notice that I had less groups. So for example, I had the category of a red pill, and then I had the category of the blue pill. Now, that is our first step. Let's identify and determine how many categories are we going to have in order to tally these results. So for example, let's think about another common example. Say I want to know the frequency of how many students had a letter grade of an A letter grade of a B, C, D, and F. Notice that each one of those boxes, the A, the B, the C, D, and F, they have become categories. They are indeed each independent category, and I'm trying to tally the results. So for example, how many students had an A, and that could be, say, 20 students. How many students had a B, how many people fit in that category, how many people can we count, the frequency, the tally of that observation. Now, notice that fewer categories is actually a good idea, because the more we try to expand, the more categories we have, the less likely we will be able to note if these differences were merely because of coincidence. So in keeping with our previous sample, say instead of those letter grades, for example, A, B, C, D, and F as a letter grade, think about how difficult it would be if I had more tallies. So for example, instead of an F, now I keep going with a G or an H or a Y. Notice that if I have more categories, that way I won't be able to demonstrate if in fact they just simply fell in those categories merely by chance. So less categories can actually reflect whether or not that tally actually fell in there because of some sort of correlation, of some sort of impact. But if I have more, then the issue with that is that I won't be able to justify my claim that, yes, they fell in this category because of that reason, and not merely because of chance. Now, generally, in this particular sense, think about that whenever I have a category. So for example, I had my A category, my B category, my C category. Notice that I want at least 5 observations in each cell. I want to be able to have at least 5 people in that tally, right? So for example, if I have a combination and then it happens that in that category or that box, there's less. So for example, we started to see smaller numbers, then the problem would be that it wouldn't be a valid category. I cannot justify that the amount of people or the amount of data points, the amount of information that was in there, I can justify that it happened because of not chance. So now this category, there's simply not enough data. We simply do not have enough data within that box, within that category, that actually reflects that category. Now, let's think about the chi-square a little bit more specifically. Now, in regards of the chi-square, I need you to consider that this is a non-parametric measure, right? It's a non-parametric measure. And what I mean by that is that we are simply not meeting the assumptions that we would in a parametric statistic, right? So for example, here we are going to do an inference. We're going to draw some conclusions from my data that is nominal, right? In other videos, we have talked about the different data scales, so nominal, ordinal, interval, and ratio. So whenever we are not able to meet the assumptions for that specific measurement, then we would need to move toward a non-parametric assessment, a non-parametric statistic. Now, in regards to the chi-square, what we are exposed to is the chi-square is going to allow us to analyze whether or not that frequency, right, the amount of tallies that I have in each category is greater than predicted by an equal distribution. And what does that mean? Well, we are going to note if there are any differences that did in fact occur, I should say, outside of chance. I want to see whether or not these have occurred outside of chance. Can I in fact say that this category is greater, that the chance of being in this category is greater than just merely chance? So that's why we are going to draw from our chi-square. Now let's continue with our slides. Now, in order to provide that type of information, let's talk about the goodness of fit. Let's talk about the goodness of fit. Now, in regards to the goodness of fit, what we're going to look into is if these values, right, the values are different, they differ, right? They are different from each category. So for instance, if I have my category of the red pill, the blue pill, and the rest of them, I want to see whether or not there are significant differences. If there's actually a difference between our selection of that category versus the second category and the rest of the categories that I might have predetermined for my assessment. Now, interestingly, let's talk about hypotheses. As you know, hypotheses are a form of prediction, right? So for instance, a hypothesis wants to establish and distinguish and whether or not there is a change, whether or not there's something different. So for instance, we would like to say in a hypothesis, every time X occurs, it's likely that, for example, Y is going to occur. We're trying to make a prediction. Whenever X occurs, then Y is going to occur. For instance, the frequency in this case is what we're going to look into. So notice that I want to make sure and I want to ascertain whether or not there is indeed that difference. So here we have the illustration of our alternate hypothesis. This is also referred to as the research hypothesis, the alternative hypothesis. And notice that H, in this regard, we have H underscore 1. So this is generally the notation for an alternate research hypothesis. What does that mean? It means that I'm trying to say there is a difference. There is indeed a difference between one of the categories versus the next category versus the next category. And here we're going to have a null hypothesis. And remember, hypotheses are predictions. So a null hypothesis is going to suggest there is indeed no difference. There's absolutely nothing that can substantiate whether or not these categories are different, if they have a difference between them. So I need you to remember that within the alternate or alternative research hypothesis, what we're trying to find out is if there is a difference. However, with the null hypothesis, we're saying there is no difference. They're actually exactly the same. Now, something that I should cover before we continue is there is always a chance that the responses, that the data sets that you're coming across whenever you're conducting your research, there's always a chance that these differences simply occur because your data, because your participants are different from each other. So sometimes we can be given the illusion that whenever participants are in our research, oh, when I'm able to accept that and reject that null hypothesis and say, there is indeed a difference, something is different, sometimes those differences can come simply because those differences are inherent to the participant. So think about the example that I gave you about a grade letter of A, B, and C. We can say there was a difference between those categories, but maybe those differences came from the individual characteristics of that participant, right? So for example, maybe the students that had an A in this exam were simply, for example, more intelligent, or maybe they had more time, maybe they had more self-control and more time management, better time management techniques. So notice that their individual differences will come into play. Therefore, there's always going to be that degree of variability. There's always going to be that degree of difference that looks and resembles that degree of difference of that alternate hypothesis. But I need you to remember that the intent of that goodness of fit, we're trying to determine if those differences were merely by chance. All right, so let's keep on with our slides. Now, let's think about the test for independence. Let's talk about the test of independence. Now, in the test of independence, we are looking for is there a difference? Is there an actual difference between them as a function of a group assignment? What does that mean? Well, if we go back to our goodness of fit, the goodness of fit, what it's trying to ascertain is there a difference between these categories? Is there a difference between categories? On the other hand, for test for independence, what we're trying to say is there a difference between them as a function of the group assignment? And what does that mean in the Queen's English, right? What does that mean in basic English? What that means is, by goodness of fit, it's just trying to determine if there are differences between each category, whereas in our test of independence, I should say, is this difference because of some form of group assignments, right? So for example, are these differences, after we find out, yes, there is a difference between the categories of, say, for example, the pills, then because of group assignment, whether I'm a female or I am a male, because of that group assignment, I'm trying to say, are these differences because I'm a female, because I'm a male, right? Because now we're looking into individual differences because of that group assignment. So for example, if we look in this example here, an answer that we could answer is, think about, because one is male, we would prefer the X color pill, right? Because one is female, one would prefer the X color pill. So notice that your frequency, the amount of individuals in that category, so for example, the amount of individuals who prefer that red pill depended upon the other category. So in this case, that would be sex. Now, as I mentioned, I wanted to cover a little bit more in detail about the symbol of the chi-square. The chi-square involves the symbol of chi, is a Greek symbol, and it has the exponent symbol up 2. Now, sometimes it's a little difficult to put to put these symbols in your text. So another way to represent the Greek symbol chi is to simply have the letter X in the italicized style, and then we are going to put a superscript 2 for that style. Now, think about the chi-square in the sense that we are trying to identify for those differences in frequency. I'm trying to find out if there are these differences in frequency. Now, the formula for the chi-square, notice that it's going to read as follows. So remember, we have, first and foremost, we're going to have the symbol of sum, right? So when you see this symbol, particularly resembles the letter M on its side, this symbol refers to the sum, right? The sum of those tallies, the sum of those data sets. So how do we read the equation of the chi-square? Well, we have the sum, and later we have the open parentheses, frequency observed minus the frequency that is expected on a close parentheses square, and then we're going to divide the sum of the frequency observed minus the frequency expected. We're going to divide it under the frequency expected. So what does this mean? Meaning that we're trying to distinguish between what is the difference between each individual cell, each individual category, each individual box, versus what we would expect that tally to be. What is it that we would expect it to be? If, for example, the null hypothesis is true, right? So for example, if there is no difference, if all the frequencies that you observe in this regard are exactly the same, there is no difference. So that is what frequency expected is. We are assuming, if you recall from our slide of the null hypothesis, we're talking about that everything is going to be exactly the same. So that is what our frequency expected or expected frequency is. Now notice that the chi-square is non-parametric, meaning that it makes use of that nominal scale. We were not able to meet the assumptions for a parametric test and parametric statistic. Therefore, we have to make use of the chi-square because it is a non-parametric test. Now, when we are thinking about a summary of what we just discussed, notice that in a nominal data scale, we're simply trying to tally data in different categories. So for example, how many people had an A in an exam, how many people had a B, and so on, so forth. And the way to analyze that nominal data, in order to analyze that nominal data, what we're going to do is conduct that chi-square. We're trying to observe the differences between the frequency that I observed versus the frequency that I expected to see. So for example, what did I expect students to get in the test, and what did they actually get in that test? As a summary, remember that the goodness of fit can be a one-way method. So for example, it means that there's only one factor. There's only one factor that is involved in the test, whereas in the test for independence, notice that we have is two-way, because now we're going to have two factors. So if you remember earlier, in the goodness of fit, we only had the selection of one factor, which was the pill, whereas in the test for independence, we had two factors because we had sex and the selection of that pill. Now, in regards to the goodness of fit, in the null hypothesis, remember that we are going to assume that all of these behaviors are equally distributed across these categories when we are referring to the null hypothesis. Again, when we are referring to the null hypothesis, we are assuming that there is no difference, that everything is equally distributed. Those tallies are equally distributed, that frequency is equally distributed in that same category. Now, let's give you an example of how we're going to set that frequency that we are expected. So in this regard, if we have two categories, right, I would expect that about 50% of all of my observations are going to be in each category, right? Or if I have 4 categories, I would expect that those tallies be 25%. So if I have 100 tallies, 100 data sets, but I only have 2 categories, I would expect that if I only had A as an option and B as an option for that test, so for example, did you pass the test or did you not pass the test? So I would expect if I only have 50, if I only have 2 categories, I should say, I should have about 50% of each of those tallies in each category. However, I have 4 categories, it would mean, so say A, B, C, and D. Now I would expect that about 25% of students are going to be here, 25% of students are going to be in the next category, 25 here, and 25 in the next category. Now, what we're actually trying to determine is my alternative hypothesis, which is, in this regard, what we're trying to do is identify there is actually no difference. There is no difference in here. I'm actually trying to discover, is there in fact a difference? They're not a difference. They're not going to be equally distributed. And how do we do that? Well, we're trying to find out if they are significant, if we have a chi-square that is significant. So let's think about the test for independence. With the null hypothesis, with the null, we're stating that both of these factors are independent, that one is not going to influence the other factor. We're also going to look into that evaluation of that interaction. If the null is significant, it means that those variables are not interacting, right? It means there's no difference. Therefore, if there's no difference, it's telling me that those 2 variables are not interacting with each other. Now, when we're looking into a two-way test, and if I pull up my slides here, let's go back to the slides. So for instance, when I am looking into the two-way, we're going to conduct an example today about how is a physical illness related to sex. So notice that now I have 2 categories, right? I have the category of an ailment, and then we have, or I should say factor, a factor of an ailment, and then we have a factor of sex. So notice a good example would be more men die of coronary heart disease. So notice that one factor, which in this case was sex, had a relationship to the second factor, which is a disease. And the same goes for women. For example, more women die from breast cancer than compared to another sex. Therefore, we can see the 2 separate. We can see the 2 different aspects and factors that went into that tally. Now let's look into some examples of a chi-square. In keeping with our example of an illness, if an ailment, let's look about which ailment would be more likely to cause death, right? So in order to do that, we're going to think about an individual, and in this case, a female, right? A woman's health profile. So let's look into some of the aspects that could be risk factors. Risk factor. So for instance, here we have that body weight could be an issue in regards to increasing that inherent risk factor. And also we have some behavioral risk factors. And in this case, smoking is a behavioral risk factor. Now let's look into, now we're going to switch from pills. We're going to switch those categories of pills. Now we're going to switch them into an ailment, right? We're going to switch them into an illness. So red here is going to symbolize heart disease, blue infection, green cancer, and then yellow is going to represent other. Now we have switched the categories. We're trying to see if these risk factors are related to this ailment categories. Let's find out what those tallies actually are. So let's consider an example in which I have indeed conducted a sample, right? So I recruited my participants and I have, for instance, remember that N represents the amount of participants, right? So in this study, we're going to find the risk factor manipulation of whether or not these risk factors make me more prone, for instance, of having heart disease, infection, cancer, or other, related to a second factor, which in this case is my sex, right? Whether if I'm a man or a woman, and see if this factor had a relationship, or I should say, not relationship. If it makes me more prone, there's more of a tally, more women are more likely to be part of each. Now, generally speaking, let's look at the category of heart disease, right? We're looking at the category of heart disease. Notice that for heart disease, about 15, right? 15 of the participants had a frequency observed, right? We observed that about 15 out of these 20 participants had an increased risk for heart disease. And the other 5, right, out of my 20, had a risk factor for other. Notice that out of my 4 categories here, right? So out of my 4 categories of heart disease, infection, cancer, and other, I actually had to eliminate infection and other aspects, right? So I had to eliminate cancer and I had to eliminate infection because simply none of the participants had a high risk for them. Therefore, I went from 4 categories: heart disease category, infection category, cancer category, and other. Now I moved into just 2 categories, my heart disease category and my other category. Now, that number, those 2 categories, I'm going to represent with the letter K. I'm going to represent with the letter K. Now, whenever we see DF, this refers to the degrees of freedom. And degrees of freedom is simply going to be the amount of participants. So my N minus 1. So for example, in order for me to calculate my degrees of freedom, I'm simply going to look into, okay, how many participants did I have? How many tallies? We had 20 people minus 1, and of course, that will be 19. Those are my degrees of freedom. Now, the frequency that I should have expected, right? If you remember, when we talked about the frequencies that we would expect, that distribution. So if I have just 2 categories, I should expect about 50% of all my participants to be in each category. Now, if we look into what we found out, right? If I manage to clear up this slide a little bit more, notice that out of the 2, right, we had 20 people divided by 2 categories. So that means that 50% puts 10 people in one box, and then the other 10 people in the other box. So this is what I should expect. I should expect to see that out of these 2 categories, the box of heart disease, right, the category of heart disease and the category of other, my frequency that should be expected is that I should see about 10 of those females here and about 10 of those females in my other category. However, when we are looking into the results, Notice that we did not have that type of result. Notice that there was, in fact, a difference because I had 15 participants, 15 individuals that were in this category. So in here, notice how it was different. It didn't remain the same. Therefore, I have to reject that hypothesis that we're going to remain the same. So notice that here, now, I would see that in that regard, if we go back to our pen, notice that for the heart disease, I had in, first of all, let's do other. So I only had 5 people. And then when it came to heart disease, I had 15 individuals. So I'm starting to see that that frequency that I observed is very different from that frequency that I should have expected, which is 10 people in each box, in each category. Now, whenever we conduct these statistics, so we would replace the frequency observed. So for example, the frequency observed for other illness minus the frequency expected, right? So after we do this equation, when we square it and later divide it by the frequency expected, which was 10, we discovered that chi-square turned out to be 5. Now, when we are looking at the degrees of freedom, and remember, we calculated the degrees of freedom with the amount of participants minus 1, right? So if we go to our next slide, it's going to represent our degrees of freedom. Right? So in this regard, the result that we had was 5, right? We had a result of 5. Now, whenever we look at the chi-square distribution, notice that our number is greater. So we have the degrees of freedom for 1 degree of freedom, and we would have the result of the p-value, and the p-value, remember, it's how significant my result is. So for example, at a p-value, and generally in social sciences, the p-value of an alpha 0.05 is what's generally accepted. Notice that I would think, and I would expect that that critical value, right, in me being able to accept or reject that hypothesis falls in 3.841. What does that mean? It means that my value of chi-square of 5 is greater than that critical value of 3.841. And this symbol here, this little triangle, as illustrated by dots, means therefore. Because my 5 was greater than that critical value at a significant level of 0.05, I can ascertain that my difference was significant. I can say with a certainty level of 0.95, I can ascertain with that degree of certainty that those differences between the category of heart disease and the category of other illness, I can say that the difference between these two was significant, that it was not by chance, that this difference did indeed occur because of some form of significance, and it was not some factor of chance. There was indeed some variability that contributed to this difference. Now, something that I would like to mention is that we also have the ability to use software to do these calculations for us. Now, if you notice in my previous sample, it was only 20 people, right? So that's a pretty easy number to tally. Sometimes we can have data sets that could be in the thousands, right? So for example, think about sampling a group of inmates in a prison, right? And a prison can have hundreds, if not thousands of people in them. So notice that now instead of moving from 20 women in this example that I gave you for research, Imagine if we had to do much and many, many more participants. So we actually had to gather data from many data points from many participants. So we actually have software that can allow us to do so. And in this case, if we go back to our slides, we are going to look into SPSS. And we're also going to talk about a chi-square calculator. Now, I will remind you that the SPSS used to have another name, right? It used to be called the Statistical Package for the Social Sciences, but later the name, it was rebranded. So they appealed to a different audience instead of social science practitioners and researchers. So now they have changed the name to Statistical Product and Services Solutions, but the process is still the same, right? So I gave you an example for women and their risk for heart disease or other illnesses. But now let's use another example, right? So instead of the tallies for risk, now let's think about a fictitious example, right? This is a fictitious example of scores of a fictitious assessment, right, for ODD, right? So ODD stands for oppositional defiant disorder. So for this scenario, I want you to imagine that we had a group of children, and these group of children were administered our fictitious assessments, right? And we tallied those frequencies, we tallied those characteristics within that assessment. And I want you to imagine that for the purposes of this mock exercise, I want you to think about, we conducted that assessment for ODD, for oppositional defiant disorder. And now we're going to tally these results. And we're going to look at them as, say, for example, mild ODD, mild presentation of symptoms, or a moderate presentation of symptoms, I should say, or a severe presentation of symptoms. So keeping that example in mind, let's look at the data. So for instance, in looking at the frequency, we would say that the minimum score that these children could have to determine if they have mild, moderate, or severe ODD in our fictitious case, the minimum that they could have had was 0, and the maximum that they could have had was 27.5. Now, if you notice, in this respect, notice that about 72 of all these participants simply did not show that amount of ODD. Now, if we move to our next example, we are going to create those categories. So think about, and I'm going to illustrate it with different colors because sometimes that's a little bit better as a visual representation. So let's think about that no ADD or ODD, I should say, is going to be represented in green, right? So we're going to have our green category, right? Our green category meaning none or mild, right? And then we're going to look into what other categories we have. Well, we determined that it's also going to tally for those results of moderate ADD. So here we are going to look into, okay, these are the participants and we're going to represent it in yellow. This is going to be my next category. So my next category would be the moderate symptomatic expression of ODD. And then I'm going to have my next category. And that next category is going to be that of severe, right? Of severe ODD. So that I'm going to represent in red. So now we have our severe category of symptomatic expression of ODD. So notice that I utilize the frequency, right? I utilize the frequency of those scores. So for example, we're going to move from none to mild to moderate to severe, and we can conduct a presentation of that data. So how do we do that? How do we do the presentation of that data? Let's go back to our slides. Now that I created those 3 bins, right? Now that I created those 3 is. Notice that for my first category, no symptoms whatsoever, is completely asymptomatic. So this is going to be my green category. Notice that that range of scores, right? If we go to our previous slide, it was about 72 participants. Now, when we're moving to that mild to moderate range, we're seeing that about 19 of those children had a score between 1.4 and 15, which would put me in the mild range. Now notice, so this would be my asymptomatic mild score. And then when we're looking at severe, we noted that the tally was a total of 7 children that scored between 20 and 27.5. Therefore, we can categorize these children as having a cinematic expression of ODD in the severe range. So if you see in this case here, we see that about 72 children were expressing either none, or I should say none to mild, and then we start moving into the moderate category. And if you remember, that was a total of 19. And then the total of the severe side in the scores between 20 and 27.5, then we had a frequency of 7. So we had a frequency of 72, frequency of 19, and frequency of 7 respectively, I should say, between asymptomatic, mild, and severe. Now, you generally wouldn't want to conduct this by hand, and here is a really good citation, and I'm going to put this up on your screen. Notice that you can reference this article here if you're wanting to have a calculation tool for your chi-square, and you can look into the goodness of fit and test for independence, and it's going to be available here. Now, here is the link for the chi-square calculator. So go ahead and pause the video and make sure to look into this calculator should you need it for further research and chi-square. So I'm going to give you a chance to pause the video and we will move on to our next slide. All right, so in continuing with our example, notice that we're doing a pie chart. So we want to represent that data that we tallied, right? So in this regard, say we had about 72% of the individuals who were asymptomatic. We had about 19 of those children who were expressing ODD, oppositional defiant disorder, in a mild fashion. And then we had about 7 children who illustrated or presented that data, those symptoms within our made up scale of 0 to 27.5. I want to thank you for your attention. Hopefully this video was informative in understanding what frequencies are, and also it helps you understand why do we use a chi-square, what is it good for, what type of information can we find. So thank you very much for your attention. Hope to see you next time.